Hello everybody, hope you guys are doing well. Today we will be starting with Coleman Introduction to Algorithms, and this is very fundamental topic when even if you're going for something like competitive programming, or even if you're trying to solve any lead code problem. This is always going to be the basics. Like this will always you will always need this. So um, the first basically we will be starting with time analysis. I mean, like big off and big T off and those topics. Then we will be learning about growing functions. What do you mean by growing? And then likewise, uh, yeah, my handwriting might not be the best, but like try to concentrate on the work. Okay. So this is basically Coleman edition 4. Let's study the preface. The preface is basically there are it says that there let's skip the preface. It's not needed. Now then let's okay. So the first topic that we will be studying is um introduction to algorithms. Like what is an algorithm? What do you need an algorithm? We will be doing the third edition. The latest is the fourth edition, I guess. Algorithm. Now in this part, we'll start you thinking about designing and assigning analyzing algorithms that is intended to be gentle. Introduction to how we specify algorithms, some of the design strategies we will use throughout this book, and many of the fundamental ideas using in algorithm analysis. Later parts of this book will build upon the base. So, like, this is a very important thing. Chapter 1 provides an overview of algorithms and their place in modern computing systems. This chapter defines what an algorithm and their what an algorithm is, lists some examples, makes a case that we should consider algorithms as a technology along with side technologies such as hardware, GPUs, the graphic GUIs, object-oriented systems and networks. Now in chapter 2, we will study the first algorithm, basically sorting. They will be there's a certain code written, and then we will try to understand. Then we will try to understand an algorithm, the efficiency, whether it is a good approach or a bad approach, so on and so forth. The role of algorithms in computing. So what are so this so first chapter that we are studying is role of algorithms. Like why do we need algorithms in the first place itself? Okay, algorithms in family and algorithm. It's a well-defined. So algorithm is basically a computational procedure that takes in some values and input and produces some values. So we can say this is an algorithm. This will have some type of input, and this will give an output. This is basically a set of basically I can say a procedure as well, or like set of instructions or procedure. Okay, now we can also use an algorithm as a tool for solving a very specific computational program. The statement of a problem specifies in general terms the desired input and output. The algorithm specifies the computational procedure. Okay. The other ways, generally we have the inputs. So this is what happens when you go to any platform like Gitcode or input. They will give you an input. So like they will give an input. They will have the output. You have to write this in Python. Okay, for example, we might need to sort a sequence of numbers into non-decreasing order. The problem arises frequently in practice and provides fertile ground for introducing many standard designing techniques and analysis. This is how we formally define the sorting problem. So how it is defined is A has given an input. So he has sequence of this is A1 to AN. A permutation, the ordering of the input sequence of that. So then what is the output? The output should be ordered in such a way that A1 is less than A2 is less than A3 and so on to the end. For example, the input is 30. So let's see, he has given the input. So let's consider a test case. The first is given is 31, 41, 59, 26, 41 and 40, 58. So what the output will be? This is the input. The output mentioned is 26, 29, 49, 50. Okay. Now in general, an instance of a problem, instance of a such an input is an instance of a sorting problem. In general, an instance of a problem consists of input satisfying whatever constraints are imposed on the problem. Because many programs use it as an intermediate step, so we said sorting is this is basically called as sorting, and many programs will use this. That's what we say. Okay. Now, because many programs use it in an intermediate step, sorting is a fundamental operation in computer science. As a result, we have a large number of good sorting algorithms. Which algorithm is best for a given application depends upon among factors: the number of factors sorted, the extent to which the items are related, somewhat sorted, possible restriction on the item values, architecture of computer, and kind of storage devices to be used. Main memory disk or event types. An algorithm is said to be correct if for every input instance it holds with the correct output. Now you're saying factors that factors that affect algorithm. Then you're saying the first is like what is the input? What input I have provided? Then like are the numbers sorted already to some extent? They might not be exactly sorted, but to some extent. They might be sorted. Then he's saying the third step he's saying is GPU, like what processor are we using? Then RAM, then HDD, hard disk or HDD, whatever. Everybody misses it. The algorithm is have to be correct. Now when is the algorithm correct? So we need a generalized algorithm. The algorithm is this is going to be generalized, like irrespective of the input. My output should always be sorted. Like what? Where? Okay. Now incorrect algorithm which might not hold on some input instances, then incorrect. So contrary what you might expect, incorrect algorithms can sometimes be useful So then, okay, we shall see an example of algorithm. When we study find algorithm for finding large prime numbers, ordinarily we will what kinds of problems are solved by algorithms. Sorting is by no means the only computational problem for algorithms. You probably suspected as much when you saw the size of this book. Practical applications of algorithms are ubiquitous and include following examples. So he's saying where we use algorithm. For example, Human Genome Project has made great progress towards the goals of identification of 10,000 genes, determining the signal. So basically, anything that requires a processing will be done with the help of some kind of algorithm. So there are multiple use cases, not restricted to sorting. There are other possible ways as well where you might be using algorithms. Now, data structure. This book also contains data structures. A data structure is basically the next important thing comes is data structure. Data structure basically the way to store and organize data. Is data structure. Even of okay. Although you can this book as a cookbook for algorithms, you may someday encounter a problem which you cannot readily find published algorithm. Then you have the access in the books in the problem. For example, the book will teach you techniques. So basically, it might happen that okay, you might have to at some point in time implement an algorithm. The hard problem. The most of the book is efficient algorithm for a usual measure of efficiency, that is speed of. There are some problems, however, for which no efficient solution is known. This is parallelism. For many years, we could count on processors, clock speed increasing at a steady rate. Physical limitations represent a fundamental roadblock to increasing clock speeds. However, because power, now see, he's saying why we need it. So then he's going to talk about parallelism and multi-thread. Okay, now algorithm is a technology. Okay, other than speed, what other as efficiency? What might given the real world example that requires sorting? One can be message folder or your image folder. What other measures of efficiency might one use in a real world setting? Other than speed, memory utilization. How much memory has been consumed? Select a data structure that you have previously seen in then discuss in strengths and limits. There are different types of data structures. One of them is an array, linear data structure. Now the shortest path in traveling salesman problems given above in I have no idea about right now. Right now we don't have much knowledge about shortest path traveling salesman. We'll see what happens. Algorithm or technique. Suppose computers were infinitely fast and computer was memory, then there was no need to so remember the goal of algorithm is not to have it's not about efficiency, it's about solving problems and getting the correct answer. That's what he's trying to say. Even if you had fast processors or something, you will still use. So the goal of algorithm, it's like a problem solving journey where you have input and an output like maths. Not maths exactly, maths you don't have an output, but then yeah. Okay. Not efficiency. Different algorithms devised to solve the same problem often differ dramatically in their efficiency. These differences can be much more significant than differences due to hardware and software. In chapter 2, we will see two sorting algorithms. The first is known as insertion and it takes roughly C1 n square time. The other is a constant, does not depend on it takes roughly proportional to n square. Okay. Okay, now this is something which is going to be important. Okay, so for a concrete example, let's put a first. Okay, now let's read this entire thing. The one sort takes C2 n log n where n signs and C2 is another constant that also does not depend upon n. Insertion sort will typically has a smaller constant factor than word sort, so that's C1 and C2. Which one of these factors? Let's write insertion sorts. So C2 n log n, then we see where insertion sort as a factor of n is a running time, word sort as a factor of log n. Okay, now what he's trying to say is efficiency. How efficiency is calculated? Like, is the efficiency. So like I have algorithm 1 and then I have algorithm 2. Suppose this takes how much time? It takes n square times to solve. This gives n square time. Now why we are measuring in terms, I'll let you know later on. This takes n log n times. This is always to the base 2. Thus we see that where n is a factor of n log n. N is the, let us assume, let's have a comparison here. I need to column that. This is 1 is n. When n is 1000. What is n square? This is n values. This is n square. This is n log to the base n. Suppose n is 10 power 4, 10 power 3. And this is 10 power 6. This is 10 power 3 into log to the base. This can be written as this one. So this 3 comes down. This will be 3 into. And this log to the base 10 is something a number, right? I have to check this. Do I have a? I'll have to wait. Let me say incognito. Let's go to and let's GPT. So let's say log base 10. How much is this? Yeah, base 2, right? It is approximately 3.3 something. Anyways, I'll just log 2 to the base 10 is. This array is mathematical, right? It is, you can calculate. This 3.3. This is something will come to 9.3 into. Now when no matter how much smaller is C1, although insertions are usually faster than method for small input sizes. Once the input size becomes sufficient, the merge search advantage of log n versus n will move. Are you saying about log n or n times log n times log n? Will be more than the compensate for difference in columns. So no matter how much smaller C1 is, C2 is, there will be always a crossover point beyond which merge sort will be faster. Let's put a faster computer A running inside sort and a slower computer B running merge sort. Each merge sort an array of 10 million numbers. The 10 million numbers might seem a lot, but if the numbers are 8-byte integers, then the input occupies about 80 megabytes, which fits the memory of even an inexpensive laptop computer many times. Suppose that computer executes 10 billion instructions per second, faster than any single sequential computer at the time of writing this. And the computer will be only 10 million. Then, so he's saying how are we going to calculate the efficiency? So to calculate that, 7 is going to use 2 into 10 power 7 9 squared, because total input is just for algorithm A, right? So then more than 5.5 hours, this will take less than 10 minutes. By using an algorithm whose running time grows more slowly, even with a poor compiler, computer B runs more 17 first time computer A. The advantage of Okay, so what happens is the algorithm will basically it will remove that constraint of hardware is gets removed over here. So even with a faster, fine, better with a better hardware, that algorithm is running slow. But here, without even using a better hardware, it is running fast. Algorithms and other technologies. The example above show that we should consider algorithms like computer hardware as a technology. Total system performance depends on choosing efficient algorithms as much as on choosing fast hardware. Just as the rapid advances are being made in other computer technologies, they are being made in algorithms as well. You might wonder where algorithms are truly important. First is computer architectures, easy to use graphical okay, so where are they used? Fast networking, both wired and wireless. Although some do not explicitly require algorithmic content, central-based web-based applications, a web-based server that determines how to travel from it will rely on hardware. So is just making like where moreover even an application does not require a thus the application rely on fast hardware. The hardware design use algorithms or GUI. The design of any GUI is an algorithm. Does the application rely on networking? Routing again relies on algorithm. What was the application to write in any language other than machine code? The algorithms are at the core. So basically, it's telling that everything, whatever you use, algorithms will be at the core. Furthermore, with ever increasing capacities, we use them to solve larger problems than ever before. As you saw in the above comparison between instruction sort and math sort is that the larger problem sizes or differences are huge. Having a solid basic of to basically improve our programming capabilities. Give an example that requires algorithmic content and application level. Suppose we are comparing implementation of instruction sort and math sort. Okay, now comparison of runtimes. Okay. Now getting started. Now this chapter will familiarize you with the framework, insertion sort. Then okay, now what does it? In this we shall typically describe algorithms written in pseudocode. If you have introduced to any, you should be evaluated. You should, if you have been introduced to any, or you should have little trouble reading our algorithms. What separates pseudocode from real code is that pseudocode we employ whatever expressive method is not clear and concise to specify. Now you're saying what is the difference between a pseudocode and an algorithm? Okay, we start with insertion sort, which is an efficient algorithm for sorting a small number of elements. Works the same way people sort a hand of playing cards. We start with an empty left hand and cards facing down on the table. Then we remove one card at a time. We check whether it is greater or smaller. Oh, this is yeah. Then you didn't mention about pseudocode, right? The pseudocode is not exactly the code. Okay. Instruction sort which makes a parental containing a sequence. Okay. The algorithm stores the input numbers in place. It rearranges the numbers. So the way it will work is. So let's see how is the working. So let's have an array. Always remember a number itself is always sorted by itself, right? Because there is nothing to compare it to. So 5 2 4 6 1 3 something. 5 2 4 6 1 3. So 5 by itself is certain. Then we go to 2. We check So I will say 5 is greater than 2. So now we'll move. So then we'll remove this conversion. So then next time what we have is track 2, 5, 4, 6, 1, 3. Similarly. Now then this is done. Now we check 5 with 4. So then now this away. This is what cancel into. So then we become 2, just 2, 4, 5, 6, 1, 3. Now we see these two numbers. Okay, we say 6 is greater than 5. Okay, here our was here we say 5 greater than 4 and say 6 greater than 5. So then do we do anything? No. This is properly ordered, right? Then we go to the next. And we check whether we check 4, 2, 5, 6, 7, 3. When it's in this device, then I say 6 greater than 1. So then now we do the moving. Then we have 2, 4, 5, 1, 6, 3. Again, now we check 6 and 3. Then we say 6 is. Then again we do the sorting. But then now see, the 3 will. But then. Oh, now when we come to this point. So what is going to happen is this one. Okay. Let's go. Yeah, you see, this 5 and 1 is not proper, right? So then even if we say 4, this is also not proper, and even if we put it over here, so we say like 1 is less than 2, 1 is less than 4, 1 is less than 5. So shifted at starting index. So I'll have 1, 2, 4, 5, 6. And I'll have 1, 2, 4, 5, 6, and 3. Even here there is an issue, right? See 6 and 3. 6 and 3 is, but then this is 5 and 4. So the correct position is here. Then our array will be 1, 2, 3, 4, 5, 6. And this is exactly perfectly sorted. 1, 2, 3. We have achieved sorting. This is sorted. Now the operation of the now he has written the pseudocode. So like always check it with the previous one as well. Now loop evaluates some correctness of insertion, so J indicates yeah. The reason why starting from the second element is, as I mentioned, the first element is always subtract, so there is no need to check. The J indicates the current being inserted in, so now he's explaining what is the J. So I have for J equal to 2 to like A of right, okay. Insert A of J into the sorted sequence 1 comma dot 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 J minus, and the I is child. This will be always running to one element. Yes. Reason being first element is sorted. So I don't want to check this. I want to check from here till the end, right? So then I say when I is greater than 0 and AI is greater than key, then I say replace it. I put A of I and A of my plus 1, decrement A by minus 1. This array consisting of 1 constitutes the current is sorted, and the remaining will be J plus 1 till n, corresponding to the pile of cards still on the table. In fact, elements will be originally in position 1 through but now in sorted order, which state that these properties formally as a loop invariant. With loop invariant to understand why an algorithm is correct. Now initialization. Okay, this is how loops work, right? So yeah, we basically will have something. So when we write a loop, first we initialize, then we do the maintain, that is the next property, and then is the termination. But it should be the loop should not run indefinitely, right? It should terminate at some point. Okay. Okay, now what he is saying is in an if else statement we indent else at the same level as its matching if. Also then he's saying how to write a pseudo code. That's okay. Then he's saying the return statement will always return the value, that is the exit. So instead of decreasing, whatever you want to do non-decreasing. Now is the important point. Analyzing algorithm. Analyzing an algorithm has come to mean predicting the resource that algorithm requires. Occasionally, resources such as memory, communication, bandwidth are of primary concern, but most often it is computational time that we want to measure. Generally, by analyzing several candidate algorithms, we can identify most efficient one. Such analysis may indicate more than one viable candidate, but we can often discard several inferior algorithms in the process. Before you can analyze an algorithm, we must have a model, the implementation that we will use, including a model for the resource of the technology and their cost. For most of these, we should use a generic one processor random access machine model of the computation. In the RAM model, instructions are executed one after the other with no concurrent operations. So what is saying that there is no switching or something happening? Strictly speaking, we should precisely define the instruction of the RAM model and their cost. So how will be tedious, noisiest, yet we must be careful not to abuse the RAM. Okay. And then we can sort in just one. If, for example, what if a RAM had an instruction that sorts? Then one instruction that such a RAM will be unrealistic since real computers do not have any such instructions, and therefore is how real computers are designed. The RAM models contains instructions commonly found in real computers such as add, subtract, multiply, divide, floor and ceiling, load and store. Okay, so what instructions are present in RAM? The RAM model contains instructions commonly found in real computers. Each instruction takes a constant amount of time. So then, okay, now see, we need to define what instructions will take how many time, right? because we are going to analyze the RAM model which is found in real computers will contain arithmetic, data movement, and control, that is control instruction. Now these all these possible instructions will take only 1 unit time to occur. The data types in RAM model are integers and floating point. For certain real numbers, however, typically do not concern us with precision. In this instance, we assume a limit on the size of it. For example, when working with inputs, we typically assume that the integers are represented by C log n. Okay. Real computers contain instruction not listed about such as instruction represent a gray area. For example, in exponent, here a constant time is exponential. The ungenerate case note several instructions are computationally powered by when x and y are real numbers. In restricted situations, however, exponential is a constant time operation. Many comprehensions have a left shift instruction which is in constant time shift the bits of an integer. In most computers, shifting the bits of an integer is equivalent to multiplication by 2, so that shifting the bits by k position is okay. Therefore, such computers can compute to power k. But we will endeavor to avoid such gray areas. So, what he's saying is, yeah, now we need to decide which instruction should we count. Now let's go to the RAM model. This is the RAM. Now, by what does he mean by RAM model is operations performed by RAM. So first is arithmetic. Then is after arithmetic we perform data store or data store and row. That is what we mentioned up. Data store. Then conditionals. And conditional and control slash condition. Now these operations can be performed by RAM, which means all of these will take 1 minute time. Which means these are unit time operations. Like they only take 1 unit to be executed by the RAM. Okay, then in RAM mode will not select, but however there is some gray area to this. Gray area is like it may so happen that some RAM may be able to perform other operations such as exponential, but then certain RAM may have the inbuilt method to do exponential, certain may not have. So those gray areas are being avoided over here. We are not and certain RAM may be able to perform left shift and right shift. So we are not dealing with that. Analysis of insertion sort. Now the time taken by insertion procedure depends upon the input. Sorting 1,000 numbers takes a longer time than sorting 3 numbers. Wherever insertion sort can take different amounts of time to sort two input sequences of the same size depending upon how nearly sorted they are. In general, the time taken by an algorithm grows with the size of the input. So it's traditional. Okay. Now it's saying how to analyze. So what we say is generally for any algorithm, the time taken is going to be measured in the input size. Is measured or slash related to how big the input is. How big. Okay. Therefore, the running time of a program is defined as a function of its input. Hence, we say if x is this is running time, and y is the input. So we can say this the running time of a program is, so we say x is a function of y. The best decision for inputs and depends upon the problem being studied. For many problems such as sorting, computing discrete FFT, or most natural measures, the number of input. For example, the array size is n for sorting. For many other problems, they multiplying the best measure of inputs as the total number of bits to represent the input in ordinary binary notation. Okay, sometimes, so you're saying that sometimes it is more appropriate to describe the size of the input with two numbers rather than one. For instance, if the input of an algorithm is a graph, the input size can be determined by the number of vertices. The address of the graph should indicate which is being used which term. The running time. The running time of an algorithm on a particular input is the number of primitive operations or steps executed. Now it is convenient to define the notion of step not are the as being machine independent. For a moment, let us adopt the following rule. A constant amount of time is required to execute each line of our pseudocode. One line may take a different amount of time than the other, but we shall assume that each takes ith line. Each each execution on the line takes time ci. So we can say the RAM model, it also reflects how the pseudocodes will be implemented in molecular computers. In the following discussion, so now we start by presenting the instruction procedure with the time cost of each statement, and then the number of times each statement is executed. For each while loop, when a for or while loop exists, okay. So now he's saying like what is so what now. So how many times? Uh, so then what he has told is let's analyze this. What he's saying. This is a single program for I. Okay, now these are primitive, right? These are the primitive operations. And for each of them, time taken is 1 minute. And then let's analyze this. So d equal to 2, result when f is j. Now let's put a parenthesis so that we can, and then I do y equal to j minus 1. Then I have while loop inside. This is all inside the parenthesis. Let's just say while I is greater than 0, greater than 2. We say similar to my new happens is 0 by minus 1. Is the key, and this is where the loop ends. Okay. Now we say this takes 1 unit time, this is 1 unit time, this is 1 unit time, this is 1 unit of time, this is 1 unit of time. Now here this a dot length is not defined, like this a dot and depends upon the array size, right? This is, so we resume. Array size is n. Okay, see, let's have something like c1, c2, c3 and so on. Okay, everything will have certain time, right? There is one instruction here as well, set aij, that is going to take 0 time. There is one instruction available which is be above here. I have something called insert. This takes 0 time. Oh yeah, so this is let's okay, yeah, okay, let's leave it this way. This is one, this is one, this is c4, c5, c6, and even this will take some time, right? This will also all operations will take time, so let's renumber them properly. Yeah, so this is c1, this is c2, c3, c4, c5, oh, c6, c7. I missed some numbers. 2, 3, 4. Or did I miss an instruction? I don't know. Oh yeah, this instruction is missed. This is C3. Oh yeah, there is one. Yeah, this is C4. Yeah, basically C3 is 0, right? So I can ignore, I can say I can write over here C3 equal to C4 equal to 0. Or not C4. So C3, only C3 is 0. Okay, now then this is C4, right? This will change. Just C5, C6, C7. Okay, now how much? So if we say if this length is n, remember we will say this is n. This will be how many times it will run, and so again, and how much time this is going to run, and -1. Similarly, this is going to run n -1 times because this is inside the loop, right? It will run till n, but in the end time it will fail. And let's come here. So I say for each n, this will run how many times? This is going to run again. It will be in some. So let this is going to take some n of j, and this is n of j -1 time, and this is n of n -1 time. But these instructions, this inner loop is going to run for every iteration of this, right? So then it will be something like n times this. This is running n times. However, how much this is multiplied by that time. So the total will be total is you add up all of them. So when I add up, then when I solve, what I'll get. So like this comes into like a sequence, right? So n minus one. This is basically n square minus n by 2, right? So worst case, now we able, so whenever you are solving any problem, we are always going to see for the worst case, unless and unless until it is mentioned that it is not going to be the worst case. Remember, the thing is, if you have a function, if you have something like if the function has n squared and another terms, the rate of that function will be determined by the term that has the highest power, your n square. So basically, you can resolve it to like n square. So this is the exact one, that is an square plus bn plus c. That is the exact result. But then worst case, remember this is not the exact analysis we are doing, right? This is going to be like an overall, like on an average kind of analysis. No, it is not the exact running time. We are not dealing with the, we don't want the exact time. We want worst to worst case what will happen. Or we need the upper bound. We need the upper bound, right? Like in in worst to worst case, what can happen? Order of growth. So yeah, same thing which I said. We won't be dealing with average time when we are solving Bitcoin problem. Yeah, you can, but then okay. So even if this is an NQ function, remember the average time. The worst case time will be always when you have the highest power contributes to that. This is why are you studying divide and conquer so early? So basically, like every yeah, so like on an average, the highest power term is the contributing term. So if you see the growth of, because we are dealing with something called as, okay, asymptotic notation. The notation is to describe running time of a long algorithm. Asymptote is something that approaches towards infinity, right? It's a mathematical concept. What do you mean by an asymptote? So we won't be considering, because see, for lower values of n, we won't get the proper analysis. You see what he's trying to say is, for lower values, for this values lower than this, the function f of n was growing in a very was decreasing, but then after when we peaked as compared to g of n, now see, now the f of n has a very, it's not a steady increase, but it's increasing as compared to g of n. So what we say is always like this, so this n value will be such that value after which the function will change, the growth will change. That's why we are always considering about we are not considering a smaller value, we are always considering something which is very big. This is basically a mathematics, like not, it's not related to programming or something. So when we always do with asymptote, so what we have is when we do asymptotic analysis, we see that the function growth will be dependent on the highest power. This is all basically which is higher, which is smaller. So yeah, so like there is something you can always search for. There is a table which indicates function growth, different functions and its growth rate. I don't know whether it has. Oh yeah, this is what I'm saying. Do we have a? There's this. Let me save it. Yeah, this is what basically I'm saying. And if it's n factorial, this has a very high grade growth. As compared, O of 1 is almost like a constant line, almost. Then consider O of 1 the least, then log n, then n log n, then n square, then 2 power n, and n factorial. There are certain tips and tricks that uh, once you start learning, right? The data structures. So we take an assumption that um, the assumption we take is so like yeah, there is an thing that needs to be we need to check here, right? What I'm going to say. Yeah. Yeah, so instructions per second, we say that the modern day processor, this is a generalized uh, thing that where we say that uh, so per second we are going to do 10 power 7. It's a rough estimate or a conception thing. Yeah, so instructions per second. Mm, this is related to more related to uh, operating systems and stuff, but we generally say IPS is 10 power 7. The symbolic meaning is in 1 second we can do 10 power 7. right? Yeah, we are always, it is 10 power 7 or 10 power 8. Yeah, right now this 10 power 9 instructions per second, but we generally consider because the base versions were 10 power 7, they had a clock of 10 power 7. Now we have multi gigahertz, so now it's not the. But then while solving problems, we want to run it. Our That's what when we said, like we said, when Corman mentions that uh, our goal is not to define an algorithm, but if we think that way, we have different computer. Everyone can own a different computer, right? For example, if you have a Mac Mini, you will have a GPU as well plus a CPU. But then not everyone has that thing, right? So what our goal is our goal is to make sure that the algorithm we write is such efficient is so efficient that it is able to work even in the worst processing environment. So 10 power 7 is basically considered to be the worst that we have, but then we make an assumption that we would be using such a bad computer. So that is one thing. And based on this, so why I'm saying is based on this we can decide there are whether the time complexity is this is basically what we mean by prime complexity is basically measuring something in terms of other cycle. Generally, we don't consider space complexity to be an issue. Yeah, so how complex it is related to time, like what factors of time, like the complexity of the how difficult is the algorithm performing when we measure it in terms of time and time complexity. So then the main goal of using this IPS is we will be saying since we are having 10 power 7 IPS, so whatever our algorithm calculates, there will be always when we solve lead code problem, there will always be an input and output thing mentioned. So using the cheat codes, we can like plug in the values in our code function and get a rough estimate of how effective that like what would be the worst case, like in worst case what can be the growth of that algorithm. We can obviously optimize it, but then worst case what will be the, remember we'll always write an algorithm for worst case and then optimize it. So okay, that's all for this lecture. Yeah, just keep this growth rate thing. This is going to be very important because this defines how the functions are. Okay, that's all for this lecture. See you guys in the next one. Thanks. Bye.